Welcome. In this little tutorial, I'm going to show you how to build a language in MPS. We'll build a little state machine language with events, variables, states, transitions, and guard conditions by reusing an existing expression language. We'll also build a second language that tests the original state machine language, and we can even run this to execute the tests. Finally, we conclude by illustrating how to build tabular notations and diagrams as part of the overall state machine story.
Alright, so let's build a generator. I'm starting from commit number 5, a second language for testing state machines. And obviously the state of the model is that we have the state machine here and the test for that state machine. Now what we want to do is we want to write a generator that generates the state machine to Java. So we put that into the state machine language, and the generator thing aspect has already been created, and you start defining a generator by going to the mapping configuration, which is, if you will, the main program of a generator. It coordinates the generation process. Now what we want to do is, from a state machine we want to generate a Java class, and so that Java class is something that lives as a root. So it is a top level concept like the state machine itself, which is why we need to use a root mapping rule. Root mapping rules are transformation rules that create new roots. And so what is it we want to transfer or transform from? Well, the state machine, right? So we're going to transform a state machine into, and now I'm adding Alt-Enter, a new template, and I'm adding a Java class. And so now here we have a new Java class. It's called map state machine, and it acts as a template from a state machine. So we can compile the language and then look at the example model and try to generate. We can do the preview generated text, and this should give us the preview of the state machine, but it doesn't because probably the test isn't handled. So for now, let's do a abandon root, where the test case, well, actually I can't see the test case here. So let's go to our test language, put a generator here, and just abandon the test case root here, just so it doesn't remain kind of untransformed in the model. It's killed, it's abandoned during the transformation process. Only the state machine itself should survive. So let's again try preview generated text, and here is the output, and it creates a Java class, well, called public class state machine, because that's exactly what we told it. Now this is not exactly what we want. We want the class to have probably the same name as the state machine from which we generate. So that's why we're attaching a property macro to this thing. It's, if you will, an instruction to the transformation engine that generates changes the value of a property. In this case, we attach it to the name, so it changes the value of the name property, and we get the node as an argument to this function-like thing here. And the node, of course, is the input which we're transforming. You can ask the type system and it'll tell you this is a state machine, because it's a state machine we're transforming from. So we're gonna grab the name of that node, recompile the generator, preview generated text, and now it's called public class traffic light, which is better. So generally, the way you write these templates is that you first write example code in Java, like literally, for example, private int current state, right? So that's a variable, a member in your Java class, and then where necessary you attach various kinds of macros, which are again, if you will, transformation engine control commands to that example code to, during the transformation, change it from the example you wrote here. So this current state is fine, right? It's the like an integer variable that keeps track of the current state as the state machine evolves, but we have to somehow represent the various states of our state machine. And how do we do that? Well, we do a private final int, and then, for each of the state we create basically a constant. So as I said, for each of the states in the input model, so we take the whole field declaration here and attach a loop macro, right? So it iterates over, in this case, the contents, and for each of the contents it generates one of these. So now it would, like, if it has 5 contents, it would generate 5 times private final int state, for always the same thing, which is not exactly what we want for 2 reasons. First, we only want to generate for those concepts that are actually states in the contents, and then we don't want it to be called state, we want it to be called the name of whatever state it is we're kind of iterating over. So we're going to attach another property macro which takes the input's name, I don't know, to uppercase perhaps, right? And again, now the node is the state because our surrounding loop iterates over those. Now we also have to initialize all of them with a different value. They can't all be 0, right? So what we're going to do is we're going to attach a property macro and just going to grab from the input state the index. Index is, if you will, the position of the node in its surrounding collection. Like, if you look at this, that thing would be index 0, index 1, index 2, and so on. So this gives us unique numbers, which is all we need. And now let's compile, see what happens. Preview generated text. No, this looks much better now. Now, what is the value of the current state variable with which we should initialize that thing? Well, we should initialize it with the field generated from that state that is the initial state of the state machine. So in any case, it's going to be a reference to a state, right? So it's technically, we need to generate a variable reference, one of these things here. But we need to kind of point it to that particular variable field, member, that was generated from the initial state of the state machine. So we need to grab from the input the states, and we want to grab the first one where it initial, right? Our initial state of the state machine. And now, how do we find the constant or the member variable that has been generated from that particular state? Well, as you can see here, we can, this little functiony thing we're writing here, it can return all kinds of things. It can return a variable declaration. So if we had some way of remembering that particular variable declaration that was generated from our initial state, we could return this. Or we could return a node pointer or just a string. So in this case, we're just returning a string, which is the name of that particular field. So what happens here is, here we generate a variable, a field for each of the states. They have a name, which is essentially the name of the state, to uppercased, right here. And here we are now resolving a reference to that field based on a name, and of course we have to make it to uppercase as well, otherwise I'm going to find it. So let's see what happens. Preview generated text, right? So this is now an actual reference to that thing. Now, in case you didn't explicitly notice, we're not writing text here. This is code expressed in another language, in this case Java base language, and it is code that has full code completion, tool support, and anything else, because what we really do is we're writing a model-to-model transformation from the state machine language model to the base language model here. And it's complete with all the tool support, and then we annotate these kind of orthogonally represented control commands that then in the transformation change the exact code we're writing here. So what else do we need? We probably need a method that returns the current state, right? So that would be a method int current state, and it just returns the current state variable. So there's nothing else to do. We don't need to templatefy it. But there is another method we have to write, which is the trigger, right? Which takes an event, where events we also represent with integers. So we probably need another one of these list of things, for the events. So in this case, we iterate not over the states, but over the events. But we still use the same kind of naming pattern and the same way of making it a unique number. So now, how does the trigger actually work? Well, it's basically the standard pattern for expressing state machines. We do a switch, which switches over the current state. So our behavior depends on the state which we're currently in. That's the whole point of a state machine. And then we're creating a case for each of the states. So do it like this. And as I just said, we're going to create one of these for each of the states. So there's going to be another loop which iterates over the states of our thing here, right? So this gives an entry for each of the states. And then, of course, because it's Java, we need a stupid break, right? So let's see what happens if we run this. Where is the preview? Here. Right? Looks like this, which is fine. And notice that we didn't have to use another one of these reference macros here to kind of point this variable reference to the particular variable that corresponds to the state we're currently generating for. And that is because there is a little bit of MPS magic that if you're iterating over the same collection of things in two places, and you refer to something from the second place that has been declared in the first, it automatically does a corresponding match, if you will. It wouldn't hurt to attach a reference macro here that says, okay, it should be the name of the of the state we're currently looping over. It's fine. So then what happens inside the case? Well, we need to find out all transitions inside that state and see if one is fired by comparing if the triggering event is the particular event we insert here or give in here, and I use an if for that. And so again, we need to do that if for all the transitions in the state. So what is this? So we are in a state. We have the contents. The contents, if you look at the hierarchy, the transition is one particular kind of content. And so we're going to loop over the contents of concept transition, right? And then what do we have to do? Well, we have to see if the event that comes in, that guy, right? If that is the event that triggers the transition. So how do we do that? Well, we know it's going to be one of these constants here, but it needs to be the constant that corresponds to the event that triggers the current transition. So again, reference macro, right? And what is it? Well, we now know it is now the current transition we're iterating over, right? And the transition, as you remember, has this trigger, right? Trigger is that thing that, well, triggers the transition. And if you look at the hierarchy, there is the event trigger, which then refers to the event that triggers it. Now, there might be other kinds of triggers. That's why we've abstracted the, trigger thing as a concept. But let's just be, let's write a non-defensive program and just assume it's an event trigger. We don't have any others right now. Make a hard downcast and ask it for its event. And now, so this is the event that triggers the current transition. And in order to kind of resolve the variable reference that refers to that event, we again return the name and do it to uppercase because we used uppercase names for events. Okay, so preview generated text. Where is it? Here. right? If the event is pedestrian button, well, then we need to do something. And the thing we need to do is we need to set the current state to the state that the current transition specifies as a target. So again, technically it's one of those state references, and it's the reference which the current transition uses as a target, and again, name to uppercase. Preview generated text. Here you go. Works. Cool. Now, again, just to drive this home, this is actually a valid program written in MPS's Java. Java does not know anything about the fact that it can be used as a template. I could write a transformation that uses our state machine language as a target. I don't need to do anything to the particular state machine language, right? Because these macros here, they are so-called MPS annotations, also known as attributes, and they can orthogonally be attached to any program node expressed in any language, which is really pretty cool. And so let's turn on the transient models and actually do a rebuild here. And now we can see what happens. So here's a bunch of steps that are used in the transformation. The first is usually just a copy of the input model, so nothing interesting happens. In the second case, the test case is still there. It hasn't been deleted yet. You know, our abandon hasn't yet executed. So that's why all the references are broken, because our traffic light has been, the state machine has been transformed into a Java program, you know, where these are actually program nodes, right, in MPS expressed. And then if we go to the next one, I don't know, nothing happened. The reason why there are some steps where nothing happens is that there are some generators that are part of Java base language, for example, that deal with MPS's proprietary version of closures and reduces them to ordinary Java code for compilation. But there are no closures in this program, so there is no change. So let's go further. Still no change. And then in the final step, the test has been abandoned. And now what happens, that from this thing, the text generation is started, which is basically a simple, you know, serialized to text thing. For example, if we look at the case, that's the definition of switch case in Java, it should have a text generator. I don't know why this one doesn't. Let's just grab something else. This one has a text generator, right, here, which simply takes the name, so that's a variable reference, so it simply outputs the name of the variable. So it's a primitive to-text serializer, which is kind of the last step in the transformation. You hardly ever write text generators. Sometimes you do, but usually you do model-to-model transformations from one MPS language to another one. So this brings me to the end of the little tutorial here on how to write this Java generator. In the next video, we are going to look at the generator for the unit test.